Based on the equation for linear momentum, you should consider linear momentum as a moving mass, where m, of course, is mass in kilograms, and v is the velocity, which is going to be in meters per second. So here's our moving mass. It's a mass and it has a velocity. And the momentum, the symbol for momentum, is a lowercase p. There's some historical reason as to why it's lowercase p. Just know it's lowercase p. And the unit for momentum is a kilogram meter per second. Nothing fancy, no names like Newton or watts or joules, just a kilogram meter per second. So based on this definition for linear momentum, let's consider which one has greater momentum. An elephant is moving rather slowly, or a pebble shot from a slingshot. Now, let's go ahead and draw these remarkably stark differences. An elephant might have a huge mass, but would have a tiny velocity because it's moving slowly. Whereas a pebble might have a small mass, but it has a very large velocity. Now, if you play this mind game and you think about these comparisons, you might come to the conclusion that they might have the same amount of momentum. Now, in general, if we double the mass of momentum, we double the momentum. And that's because in order to keep this balanced, if I go ahead and double his mass, I end up doubling the momentum. There are no square roots, there are no 1/2s, there are no squared powers like with kinetic energy. It's a simple linear relationship here that we're seeing. So if I double the mass, I double the momentum. If I double the velocity, I double the momentum as well. If I double the mass and the velocity, I have to multiply the momentum by 4. So it ends up being 4 times stronger, our momentum, if I end up doubling the mass and doubling the velocity. I need you to consider for a moment football players. I remember having a physics student a while back, and he was a rather smaller student, and he played football, and he knew that he had a smaller mass compared to the other players. So how did he compensate for that? He did a lot of training on his velocity because he knew that what he couldn't make up for mass, and he tried eating and gaining mass. He could compensate by increasing his velocity. So he did a lot of training with his speed, and that made a difference on the field. He was able to tackle and make some good collisions because he was fast. So again, just bringing home the idea that momentum is a moving mass. It's a mass times a velocity. So in a weird historical twist of fate, Newton's second law was actually originally written by Newton, not as we are accustomed to. It was actually written more like this, where we know by definition the velocity over time is acceleration. So if we were to take this acceleration and replace it with its kinematic value, velocity over time, delta v over delta t, and then we did some rearranging around, you would see that m times v is momentum. And we come to this conclusion that force, or the net force experienced by an object that goes through a change in momentum, is that change in momentum with respect to the change in time that it takes for it to happen. Now this change, remember, means that there is a final and an initial. We have 2 points of consideration here. So this is Newton's second law historically rewritten to our designs. And if I multiply both sides by delta t, I get this right here, which ends up being our average force times delta t is equal to the change in momentum. So looking at part A, we have an object experiencing momentum of 30 kilogram meter per second. Remember, we don't have a nice fancy unit for this. That is the unit for momentum. In 10 seconds, calculate the force, or the average force exerted on it. So I'm looking for this F, which means I do the momentum divided by the time. So if we look at this, that's momentum divided by the time. Well, look what happens to the time. Look at the units, right? because some of you are still hurting with your units. The seconds do not cancel out because you're going to get a kilogram meter, and that is not a unit for Newton. So yeah, 30 divided by 10, whoop-de-doo, that's 3. But we're not pre-algebra students. We're AP Physics. So let's look at the units. We have a kilogram times meter over second divided by second over 1. And then if we keep flip change, and that gives me a kilogram meter over second squared, and that is a Newton. That is the appropriate unit for force. So even though A was mathematically simple, we just divided the numbers, be aware of the units. Part B, we are given the force and the time. I want the momentum, and so I'm looking for P, so that's the 50 newtons. But let's write Newton as a kilogram meter per second squared, and then multiply that by the time, which is 3 seconds. We get 150 kilograms meter. One of these seconds cancels out this one here, so that's a kilogram meter second, and that's the appropriate unit for momentum. Part C, we're looking for the time, calculate the change in time. And so that's going to be the change in momentum over the force. That would be 25 kilograms meters per second divided by 50 newtons, but a newton is a kilogram meter per second squared. Now, if we want to do this appropriately, we could go ahead and do the units as a kilogram meter per second divided by a kilogram meter per second squared, and then keep flip change. Cancels, cancels, cancel, 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 cancel. Left with the second, which is the appropriate unit for time. And 25 divided by 50 should be 0.5 seconds. We usually expect with problems like this involving momentum, impulse is what we're going to call this in a moment, and time. These times are going to be very, 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 very small. Okay, so expect things like less than 1 second, definitely in a decimal range. When there's a collision, right? When two people are boxing and the glove hits the face, we're talking milliseconds here. When the ball hits a tennis racket or it hits a baseball bat, we're talking milliseconds here, even microseconds in some cases. Okay, so just keep that in mind. So in problem 2, part B, we ended up using this equation where momentum is equal to force times delta t. And if I have a constant force acting on an object, then it's called an impulse. So we have impulse and sometimes some books or some assignments will call it J. It depends on if you're a physics major or an engineering major. Mathematicians, we don't do much with impulse. It's just a thing that real people deal with. So it might be a J or it might be an I. Right now I'm going to refer to it as I. F times delta t. Now this happens to have the same units as momentum. Now if we look at this, we're pretty much saying that a change in momentum is the same thing as impulse. So impulse is a change in momentum. So momentum and impulse, let's talk about them. Momentum is mass in motion, and any moving object can have momentum. But now let's get more technical. If an object's momentum is changing, then an object's change in momentum is equal to its impulse. So impulse is a quantity of force times a time interval. Impulse is not equal to momentum itself. Rather, it's the increase or decrease of an object's momentum. So if we have a change in momentum, then impulse is the quantity that is responsible for that change in the object's momentum. Now, of course, they happen to have the same units, and they happen to occur during the same situations and circumstances. But as far as mathematically working with these ideas, it depends on what we're given, right? Are we given mass and velocity for momentum, or are we given a force or a change in time as far as impulse is concerned. This idea of momentum is actually an impulse is very, very fascinating. We have lots of explanations for this. Boxing, for example, you had boxing back in the day. It was pretty much bare fists, and the problem is that people were dying because of brain injuries, brain damage. And so what happens is that over time, you have padded gloves. Now, the padded gloves aren't so that you don't cut your face or that you bruise more necessarily. It is to actually add a delta T. You can read the explanation, which is a lot more eloquent, but let me give you some idea here, right? So for all purposes, we have F times delta T is equal to the change of momentum, M times V, but let's assume that the face is still, and then its momentum is going to change because of the punch. So look what happens here. The punch is going to be our force, and the M times V, well, that's our face, and that's not going to, that's our face. All right. Now, what happens mathematically speaking? You can use some calculators if you need to, but you should probably be in trig pre-calculus, calculus at this point. So work with me here. Work with me here. If this number down here, this is a fraction, right? If this number down here is small, tiny, right? Then what happens to this entire number, right? Like if I have 1,000 divided by 1, I get 1,000, right? What if it's 1,000 divided by 0.5? Now it becomes 2,000. You see, this fraction is getting bigger. So what if it was 0.01, right? It's 10,000. The problem is that as these numbers on the bottom get smaller, my answer becomes bigger. So if the amount of time it takes for my head to receive a punch and for it to go from 0 to however fast I'm going, in particular, not even my face, my brain, right, physiologically speaking, if it has a small amount of time for it to change its velocity, then I'm experiencing a great amount of force, and that's going to go ahead and result in the brain becoming dislodged. If we add padding to our glove, however, we increase this delta T. And if we make this bigger, then the fraction becomes smaller, and the force that I'm experiencing is going to be smaller. So, wearing the pad doesn't keep your face prettier. Wearing the padded gloves makes it so that you increase your delta T and therefore decrease the amount of damage you receive. Folks, seat belts, they're not there to quote unquote keep your body from flying out the glass, although that's very much true as well. The seatbelt is going to hurt, but the seatbelt in the car is meant to add delta T so that your brain doesn't become dislodged. Airbags. Airbags aren't there to protect your nose from breaking. Spoiler alert, the airbag will break your nose. Okay? However, that delta T on the airbag is going to increase the denominator and therefore make the force that you receive and therefore the change in velocity of your face be a lot less. And so you will not become brain damaged because of it. You're going to break your nose, break your chin bone, break everything else, hopefully have a decent recovery, but you'll be able to recover. That's the idea behind the seatbelt and airbag combination. And we can go on, and I would invite you to look around nature, look around places, consider that really the secret to momentum, force, impulse is increasing delta T. You remember all those little egg drop labs where you were supposed to drop an egg and it wasn't supposed to crack? The secret was delta T. If you could, and that's where you found out that using grass, right? If you actually took an egg right outside right now and dropped it on grass, it probably wouldn't break because of the delta T. The grass cushions the impact, it slows down the velocity, and then it's all good. Superheroes. Go watch a superhero movie and look at what they're doing with their delta T. Is Superman, is Batman, is Spider-Man? Spider-Man, you remember Gwen Stacy. if you're going to save somebody, you have to give them some delta T. You can't just grapple their body because they're falling, they're accelerating downward. You can't just grapple their feet and pull them up instantly because you save their body, but they're brain dead by the time that you bring them back up. You have to give them some slack. You have to give them some delta T, like the raw egg on the grass. Okay, if you jump into from a bridge into a river, they say that it's like hitting like a block of cement. Well, it is depending on how you land on it. If you dive into it, that's why when you dive into a body of water, you are increasing your delta T. If you don't do that, if you belly flop from a bridge onto a river or a lake, then it is like hitting cement because your delta T is so tiny, the force is so high, and now you're brain dead. Okay, it isn't that your bones all crumbled. It's just that the change in the velocity was just so quick and so much that your brain couldn't keep up with it, and you're done. Okay, so anyway, just wanted to really emphasize this idea conceptually of delta T. Increasing delta T, decreasing delta T is definitely going to affect a lot of things. Okay, enough talk. Let's fight. Let's do some math. So here's the impulse momentum theorem. Under a single constant force, we can come to this conclusion that impulse, right, is a change in momentum, and that I could express this in terms of this. Now, keep in mind that this is one single mass, so the mass hasn't changed. The mass remains the same object, and in most likelihood, at least in this class, the mass has kept all of its mass. In real life, if we're talking, for example, in a car crash, the car may lose some of the mass, right? Or if we're actually talking about one of the big uses of impulse is in terms of aerospace engineering, and if we're launching a 2-stage, 3-stage rocket, in the process of going up, we're losing mass because we're burning gasoline, or we're burning fuel, and so the mass will change. We have very much more complicated formulas for that and appropriate ones, including ones that have something called specific impulse. But we're going to keep things simple. The mass stays the same. So here we have a car hitting a wall and then rebounding off. Now, it didn't incur some damage, but we're going to assume that it didn't lose any mass. And the person was wearing their seatbelt. Excellent. So we didn't lose them either. The mass of the object is 1,500 kilograms. Make sure that when you do these problems, they are in kilograms, not newtons. And furthermore, one of the biggest scales to have here is something that we kind of picked up with Newton's laws, the idea of having a positive and negative direction. So in this case with the before, we're claiming that going left is going to be negative, and we're claiming that going right is going to be positive. Okay? And this is very important, especially when we have multiple objects. In this case, we just have one object, the car, with an immovable object, the wall. Now, we want to find out the impulse delivered to the car during the collision. Now, the impulse can be the change in momentum. So let's go ahead and do that. Now, it's important to use the right spots and the right signs, because having this minus in the formula and this negative with this velocity will end up resulting in a positive for us, and it'll give me an impulse of 26,400 kilograms meter per second. So that's our impulse for part A. Now, it's interesting to start making some observations and note a few things. Notice in this case that the velocity going into the wall is not the same as the velocity going out of the wall. And so we'll talk about that in the near future here, about what happened to some of that energy. However, part A, we got our 26,400. Now, part B, they want the size and direction of the average force exerted on the car. Wait, what exerts force on the car? The wall does. Remember Newton's third law. Newton's third law says that if a car hits the wall hits the car back. And so that's what's happening here. Now, the average force, we said that the average force times delta t is equal to the impulse. And we found the impulse already right here. So the average force would be the impulse divided by the time that they gave us. Remember, I kind of warned you about the times are going to be small, right? So the crash doesn't happen very long. It's just a few milliseconds. And if we put this in a calculator, we get a pretty big force. We get 176,000 newtons. And that's because this was so tiny. If we happen to have, if we want to play the what if game, what if we went ahead and designed a car where if there was a sensor, right? I'm talking to you future engineers here, especially automotive engineers, that if it comes within a certain distance, or there's a certain high velocity that you're going and a certain distance, they would go ahead and actually push out an airbag, right? So not just the face airbag, but an actual car airbag. Because by doing a car airbag, what we would do is we would theoretically increase its delta t, and therefore we would decrease the force that the car experiences, and as a result, the car would have less damage, and you, the human, would also experience less hurt as well. Now there's an idea, huh? Now the only problem is trying to make it so that it doesn't just go off every time, right? But that's what you guys are for.